start recording the meeting. Should be recording. Okay, recording started. Okay, now we'll just wait for 4 o'clock. And now can you see the slides?
Yes.
Perfect.
Sit in the back. I'll be the
Glad to see we've got a good turnout in the office here. I was worried it would just be me sitting.
never leave you alone.
Quite nearby. I think you'll recognize a lot of the pictures in the seminar. Quite close to the office.
Nothing to do.
I didn't expect you to.
Kind of bored, you know, because nothing to do.
Just waiting for 4 o'clock. Okay, so it's gone 4 o'clock there. But I think we'll maybe just wait a minute or two longer, just in case anyone's running a bit late. Sorry to keep you guys waiting.
Are you expecting quite a turnout?
Fair turnout, we had more than 50 RSVPs, so I think everyone pulls through. Cool, now, how many participants do we have?
23.
Let's just give it a minute or two longer.
Good. Do you not demo on that? It's really, I did it last week, but I didn't know you guys could yeah, okay, but that's
Okay, I was trying to find.
let's keep this week's history there. I'm going to have my so I usually wait for her to do my job.
I don't think so. But she may have to double check.
Let's just join in, I think we're gonna just wait another minute or two. Let's join, and then we'll begin.
And try and sort things out. Thank you so much.
Yeah, let's keep you.
Okay, thank you.
It seems like we're using words maybe.
Yeah, I think if we've got to it's going to find us.
All right, thank you so much.
Thank you for this.
Okay, it's about 2 minutes past 4. I think we're going to get started with the seminar. So, first of all, I'd like to welcome you all to the seminar on Slipping Through the Cracks, and this is a seminar, as you know, on the use of crack width requirements in marine reinforced concrete structures. And my name is Nick Elias. I'm a graduate engineer at PRDW. And before we get going, let me just introduce. So, as I mentioned, I'm a graduate engineer at PRDW. And for my entire life, really, I've loved the sea, and I've also been fascinated with building things. And the combination of these two interests led me to a career in coastal engineering. And before I started work at PRDW, I did my undergrad degree in civil engineering at UCT, and then I followed it up with a master's in structural engineering. And my master's research and my dissertation focused on the use of crack width requirements, and it's through that research that I'm hosting this seminar today. And importantly, my master's research was funded by the Harry Crosby Foundation, and it is through the Harry Crosby Foundation that I have the incredible opportunity to host this seminar. So throughout my research, I noticed that when it comes to the crack width requirements, there's a tremendous disconnect between the practical and the theoretical. And the aim of this seminar is to bridge this gap and to evaluate the effectiveness of the crack width requirements while doing so. And my hope and my aim for the seminar is that everyone here will leave having learned something new. For the engineers in the audience, I hope you come away with a better understanding of the theory behind the crack width requirements. And for the academics and the researchers in the audience, I hope you have a better understanding of some of the practical issues and requirements for the crack width requirements. And for everyone, I hope you all come away with a better understanding of some of the issues with the crack width requirements. So, as many of you would have seen from the invite sent out for the seminar will be split into 2 parts. The first will be a presentation on where we are with crack width requirements at the moment. And this will be split into 3 parts. The first will be a background section, mostly on the theory of the crack width requirements. And then I'll also look a bit at the requirements themselves and their history and how they were developed. The presentation will end off with an evaluation of the crack width requirements, based both on my research and also information that's available in the literature. And after the presentation, we'll have a workshop on the crack width requirements in practice. And this is where you all contribute something to the seminar by participating in what will hopefully be a livelier discussion. And various talking prompts will be used to lead the discussion. So just before we dive in, after this welcome and introduction, I'll start with my presentation on crack width requirements. We'll then have a quick 5-minute comfort break after the presentation before moving on to the workshop or the discussion. And then we'll end off with 10 minutes just to close things up and for me to say thank you. So, without any further ado, let me get started on the presentation. So, let's go back. So, as I mentioned, this seminar or this presentation will be split into 3 separate parts. And these are what we know, what we do, and what we think. So let me dive in to what we know. So this section is more of a background theory section where I discuss some key concepts that will be necessary to understand the second and third parts of the presentation. And we're going to look at marine reinforced concrete structures in general, their durability, we're going to look at cracking and the effects of cracking on durability, and then we're going to look at some specific things to do with the effect of crack width on corrosion rate. So, as many of us here know, reinforced concrete is used very widely in the marine environment. And for example, just in Cape Town alone, we can see reinforced concrete used in breakwaters, jetties, sea walls, quay walls, and many other structures. But the biggest issue for concrete or reinforced concrete in the marine environment is chloride ingress. Now, concrete is an alkaline material, and this means that usually when we put reinforcement in concrete, it's protected by a passive layer. However, chlorides, which are naturally present in seawater, and chlorides are really the bad guys in the story, they penetrate the level of the reinforcing steel, destroy the passive layer, and this leads to the initiation of corrosion. So once corrosion is initiated, it proceeds as an oxidation reduction reaction with iron being oxidized at the anode, resulting in the formation of rust, and water and oxygen being reduced at the cathode to form hydroxyl ions. And I'm going to stop the chemistry lesson there and not go any further, but the main thing I want to point out is that corrosion depends on the presence of oxygen and moisture at the cathodes, or at the cathode, and on the ability of electrons to travel from the anode to the cathode. And we'll see why this is important later. Furthermore, we also distinguish between two possible types of corrosion, depending on the arrangement of the anodes and the cathodes. The first type is microcell corrosion, where we have lots of small anodes and cathodes placed closely together, and this results in the formation of a relatively uniform layer of rust. The other type of corrosion is macrocell corrosion, and in this type of corrosion we have relatively small anodes with relatively large cathodes that can be up to quite a distance away from the anodes. And this type of corrosion, which is what typically occurs in the marine environment, is very dangerous because it leads to large localized losses of steel at the anode, and this is referred to as pitting corrosion. Now, another really important concept in durability of marine reinforced concrete structures is service life. And the service life of a marine reinforced concrete structure can be defined as the length of construction of the structure until it's is no longer usable. And sorry, let me just say that the service life of a marine reinforced concrete structure can be defined as the length of time for which the structure is fit for purpose without the need for excessive repairs or replacement. And service life can therefore be seen as a quantitative measure of durability. And for reinforced concrete structures, we typically split service life into two stages. The first is the initiation period, and that's the time from when the structure is built until corrosion begins. And the second stage is the corrosion propagation period, and that runs from when corrosion is initiated until the corrosion damage becomes unacceptable and we can no longer use the structure. Now, I think let's move on to cracking itself. So, as many of us know, concrete is very strong in compression, but also very weak in tension. And this means that we often encounter the situation where the tensile stress in the concrete exceeds the concrete's tensile strength. And whenever this happens, cracking occurs. And there are many different causes and types of cracking. However, here we're going to focus on just three: flexural cracking, shrinkage cracking, and thermal cracking. Flexural cracking occurs whenever we have bending in beams, slabs, or columns, as this bending can lead to the development of tensile stresses and therefore possibly cracks in the concrete. And this kind of cracking is typically seen in the sagging and hogging regions of beams and slabs. And we can actually see this all around us. For example, at Cavendish Square here in Cape Town, we can see hogging cracking over all the supports. Whenever we have columns, we have I-beams running between those columns, and then hogging cracks in the concrete over those I-beams, which I think is quite interesting. Now, the second type of cracking, shrinkage cracking, is quite different to flexural cracking. The moisture is lost from the concrete, and this moisture loss leads to a loss or decrease in concrete volume. And if this decrease is restrained and the concrete is wanting to contract but it can't, that places tensile stresses in the concrete, and that can lead to cracking. And there are four different types of shrinkage, and therefore shrinkage cracking, that we can get, that being plastic shrinkage, drying shrinkage, autogenous shrinkage, and carbonation shrinkage. However, of these four, only drying shrinkage is particularly relevant to us for crackwork design. And we can also see this kind of cracking all around us. For example, on the deck of the Simonstown jetty, we can see both drying and shrinkage cracking. Plastic shrinkage, I'm sorry. The third type of cracking, thermal cracking, is quite similar to shrinkage cracking because it's also caused by a volume change. However, the volume change occurs as a result of temperature changes. And of course, if these temperature or these volume changes are restrained, again, we'll have tensile stresses developing in the concrete, and because of that, we might have cracking. There are also two distinct types of thermal cracking: cracking due to concrete hydration heat, or cracking due to ambient temperature fluctuations. And this type of cracking is quite common for reinforced concrete walls, where we have foundations that provide very rigid restraint. So, recall that the service life of a marine reinforced concrete structure is typically split into two components: corrosion initiation and corrosion propagation. But one of the main things that cracking does is it allows for the rapid ingress of chlorides, oxygen, and moisture to the level of the reinforcing steel. And this means that cracking typically leads to instant or near instant initiation of corrosion. And this is significant, as it means that the service life of a cracked reinforced concrete structure in the marine environment is limited to the corrosion propagation period only. And propagation begins in cracked concrete. It can occur in three possible corrosion cells: either microcell corrosion, where we have both anodes and cathodes being located in the crack, or in macrocell corrosion, where we have either the anodes or only anodes at the cracks, or in cases where we have lots of cracks, we can have both anodes and cathodes at the cracks. However, once corrosion is initiated, the extent to which it continues is quantified by the corrosion rate of the reinforcement. And the effect of cracking on the corrosion rate is highly complex and depends on several factors, such as crack width, the orientation of the crack relative to the reinforcement, the frequency or the number of cracks, and also the activity of the crack and the cover depth and quality of the concrete. However, despite the complexity of the cracking problem and all these different factors, current design codes of practice focus only on crack width. And this is even though this topic has been researched for more than 5 decades. And after more than 5 decades of research, no clear relationship between crack width and corrosion rates has ever actually been found. Instead, what we see in the literature are two competing schools of thought. And the first school of thought believes that there is no relationship between crack width and corrosion rates, whereas the second school of thought, completely opposite to this, believes that wider cracks do indeed result in increased corrosion rates. And the first school of thought was championed by researcher A.W. Beebe in the late 1970s. And he observed that cracks typically intersect the reinforcements, leading to the type B macrocell corrosion that we saw earlier. However, remember that for corrosion to occur, we need both oxygen and water at the cathodes, and electrons need to be able to travel from the anodes to the cathodes. But Beebe pointed out that as the cracks are only located at the anodes, neither the amount of oxygen and water at the cathodes, nor the ability of the electrons to travel is a function of crack. It therefore follows that corrosion rates shouldn't be a function of crack width. And there's some experimental evidence to support this. For example, Yu et al. And Chen et al. Both found that the most severe corrosion didn't necessarily occur at the widest cracks. However, the second school of thought is generally based on more recent research. And most of this research has found that there is indeed a relationship between crack width and corrosion rate. And as crack width increases, so too does corrosion rate. And these findings were attributed to the fact that larger crack widths result in larger exposed steel areas, and thus larger anodes, and also in greater chloride concentrations at the reinforcing steel. And furthermore, when we have larger cracks, there's also a reduced chance of those cracks healing or sealing themselves. And Beebe, in the first school of thought, also didn't account for the fact that if we have type A or C corrosion, then the amount of oxygen and water available for cathodes will be a direct function of crack width. So ultimately, we can see that there are valid arguments for both schools of thought. And to this day, the relationship between crack width and corrosion rate remains unclear. And it's actually unlikely that we'll ever have a definitive or clear answer. But these days, the general consensus does tend towards the second school of thought. So, in conclusion on what we do, there are many different types of cracking. The service life of a marine reinforced concrete structure is typically split into two stages: corrosion initiation and corrosion propagation. Now, cracking causes instant or near instant initiation of corrosion, such that the service life of a cracked marine reinforced concrete structure is typically limited to the propagation phase only. Also, we know that the effect of cracking on the corrosion propagation phase is high. And finally, despite decades of research, no clear relationship between crack width and corrosion rates has ever been found. Also, here are some of the references I referred to in this portion of the presentation, if anyone would like to go back and look in more detail. Now, before I start with the next section, I'm just going to grab a quick bit of order. So, moving on to the second part of the presentation, what we do, this part of the presentation is all about the crack width requirements themselves. And first of all, because of the major issue of chloride ingress, durability design plays a major role in the design of marine reinforced concrete structures. And a big part of this durability design is accounting for the presence of cracks and trying to mitigate their impact. And the first way that we do this is using appropriate reinforcement and joint detailing to try prevent the formation of cracks in the first place. For the same reason, we also try to use good construction practices to prevent cracking. But it's not always entirely possible to prevent cracking. And in situations where we can't prevent cracking, we use the crack width requirements. And the crack width requirements are based on the philosophy that if we limit cracks to a certain prescribed value, then the concrete or the reinforced concrete will be as durable as if it were uncracked. And the limiting crack width is a function of the purpose and exposure environment of the structure. For reinforced concrete structures in the marine environment, the crack width limit is typically 0.3 millimeters. And we limit cracks for two different kinds of cracking. The first is flexural cracking, and the second is drying and thermal shrinkage cracking. And because of the similarities between drying and thermal shrinkage cracking, we sort of lump them together into one category. And currently, when designing to meet the crack width requirements, for flexural cracking, we use EN 1992, and for drying and thermal shrinkage cracking, we use the Syria C766 guidelines. However, this is likely to change in the future based on the recommendations of both the FI. However, I believe if we are to understand where we're going and where we are now, we first need to know where we are coming from. So this whole thing of crack width requirements actually goes quite far back to the 1950s when the first formulas for predicting crack width were developed. But it wasn't until 1966 that the first really impressive formula was developed by a researcher, Borges. And this formula was the first one to account for the effective concrete cover, bar diameter, and the effective reinforcement ratio on crack width. And based on this formula, we see crack width requirements first being introduced in the 1980s. And since then, there haven't been any major updates to the crack width requirements. And it's worth noting that both the Eurocode 2 requirements and the Model Code 2010 requirements actually still use that Borges formula from 1966, and with only some minor changes to a couple of small factors here and there. But basically what we're using in crack width design at the moment comes from something that was developed in 1966. Now, I'm not going to dive too deep into the formulas behind the crack width requirements or predicting crack widths, but I want to point out that both the Eurocode 2 and the FIB Model Code 2010 use very similar crack width formulas. As I mentioned before, those were based on the same formula developed in 1966. And the formulas in those codes ultimately allow for four methods of reducing crack widths. The first is to increase the provided reinforcement area. The second is to reduce the bar diameter and spacing. The third is to reduce the concrete cover. And the fourth is to use deformed or high bond bars. Now, the first and second options are quite achievable in practice, but the third option is really not advisable because in the marine environment, we generally want to use the biggest concrete cover depth we can. So we can't really use the third option. And the fourth option isn't really an option because typically we use deformed or high bond bars anyway. Then looking at thermal and dry and shrinkage cracking, the Sirius C766 guidelines use a modified version of the Eurocode 2 crack width formula, and the methods for limiting cracks are therefore the same as for flexural cracks. But it's important to note that the Sirius C766 guidelines differentiate between three different kinds of restraints and cracking. That's edge restraint, as is typically found in walls, end restraint, as typically is used for beams and slabs, and internal restraint, which is relevant for very massive, thick concrete members. And also quite important to note is that the requirements of the C766 guidelines frequently result in conservative assumptions and excessive amounts of reinforcement being required. And this is particularly true for cracking due to end restraint. So, in summary on what we do, the crack width requirements are used to limit the widths of cracks which cannot otherwise be avoided through good detailing and construction practices. Crack widths are limited for flexural and dry and thermal shrinkage cracking, and there have not been any significant changes to the crack width requirements and prediction formulas since they were first introduced in the 1980s. In practice, there are two ways in which crack widths can be limited to meet the requirements. The first is to use steel, and the second way would be to use smaller diameter rebars packed closer together. Then finally, the crack width requirements may result in the use of excessive amounts of additional reinforcing steel, and this is something we'll see a lot more in the next section of the presentation. And this is just a reference for the history of the crack width requirements. It's quite a good read if anyone would like to go into more detail. Just going to grab a quick bit of water. So, moving on to the third section of this presentation, this is really the crux of the matter, where we evaluate the crack width requirements. And this will be based both on my research and also on the opinions that are available in the literature. So, there are actually quite a few issues with the crack width requirements highlighted in the literature. The first of these, as we've already seen, is that there is no clear link between crack width and corrosion rate. But the fact that the crack width requirements often favor the use of smaller bars at reduced spacing is also an issue, because this can lead to higher corrosion rates when we have smaller bars packed closer together. And there's also a big philosophical issue with the crack width requirements, because the requirements say that if you limit your crack width to, for example, 0.3 millimeters, then your reinforced concrete is as good as if it was uncracked. But more recent research has found that even small cracks with widths below the requirements actually result in significant corrosion. And so this means that even if you do limit the cracks to, for example, 0.3 millimeters wide, they may not be, or the structure may not be as durable as an uncracked structure. There's also some practical issues with the crack width requirements. For example, the studies they're based on were often quite limited. And there's quite a bit of ambiguity and conservatism in the requirement. And finally, there are also some issues with the formulas themselves, which are known to not always be that accurate. So, as I discussed earlier, if you're designing a reinforced concrete structure in the marine environment and you find that your crack width is bigger than the limit, there are two things you can do. You can either reduce the bar diameter and spacing, or you can increase the provided reinforcement area. And the focus of my research, and therefore this presentation, is to evaluate the effects of these two choices on the durability, cost, and environmental sustainability of marine reinforced concrete structures. And this will lead to an overall evaluation of the effectiveness of the crack width requirements. And before I dive into the evaluation itself, I just want to point out that the research I'll be presenting here comes from two sources. The first is my original master's research, which focused more on the effects of the first option, reducing bar diameter and spacing. And in my master's research, I looked at Eurocode 2 and Sirius C660 guidelines, and I made detailed calculations of service life, life cycle cost, and embodied carbon. However, since starting work at PRDW, I've noticed that option 2 is quite often used to meet the Krackworth requirements, and so I carried out some subsequent research looking more at option 2. And in the subsequent research, I also used the Model Code 2010 and the Surya C766 guidelines. And I didn't perform detailed calculations, but I made some high-level calculations of service life and provided areas of reinforcement. Now, in my original research, I designed 2 sets of typical marine reinforced concrete members. One set I designed with the Krackworth requirements, and the other set I designed without. And I then estimated the service life, cost, and embodied carbon for each set of members. And I looked at 2 kinds of typical members. The first was a shiploaded crane rail beam for a coal export jetty in Matola, Mozambique. And this design was dominated by flexural cracking. And the second kind of member I looked at was a precast crown wall unit for an armoured quay in Rupert's Bay, St. Helena Island. And this design was dominated by thermal and shrinkage cracking. So between the 2 members, I got a good picture of both of the kinds of cracking we typically design for. Then just some detail on my methodology and the calculations I did. For the service life modeling calculations, I considered the corrosion propagation period only, and I defined the length of the corrosion propagation period as the time until 15% of the steel cross-section had been lost to corrosion. And I calculated 2 corrosion rates. The first was a base corrosion rate, using the corrosion rate model developed by Otieno in 2014. And the second corrosion rate I looked at was a modified corrosion rate, which accounted for changes in bar diameter or the effect of changes in bar diameter and number. Then for the costing components, I calculated the life cycle cost of each member as the sum of the costs of construction, maintenance, and repair. And I also considered the use of crystalline admixtures or hydrophobic coatings as alternative methods as opposed to the Krackworth requirements. Then finally, I quantified environmental impacts using embodied carbon, and I calculated embodied carbon values using the iStruct-E How to Calculate Embodied Carbon guide. And in doing so, I only considered product stage emissions. Then, in my subsequent research, which can effectively be seen as an expansion of my original master's research, I used the same members as in the original research, but I looked at all the possible combinations of bar diameter and spacing to meet the Krackworth requirements. And I also considered the use of the FIB Model Code 2010 and the updated Surya guidelines, as I mentioned earlier. And yeah, service life was calculated as in the original research. So before we dive into the evaluation itself, just a final note on, as an engineer, when we're choosing between the 2 options, what factors do we actually look at? And I've summarized them here, that if we reduce the bar diameter and spacing and use option 1, we typically need less reinforcement to meet the requirements, and this will result in lower costs. However, this isn't always practical, because if we reduce the bar spacing too much, the structure may not actually be constructible, it may not be easy to construct. So with that in mind, if we choose the second option and increase the provided area of reinforcement, we'll of course need more reinforcement, and this will result in increased costs. But this will be more practical with better constructability. And also I've picked up that in the marine structures industry, there's a general trend towards conservatism, and this usually favors the use of the second option. So ultimately we can see there are pros and cons to both options. And also want to note how in choosing between the 2 options, durability does not typically play a direct role in the choice. So looking at the findings of my research, first of all, I want to look at the effect of the Krackworth requirements on design. For the jetty beams, to meet the requirements using option 1, I changed from Y40 bars to Y32 bars. And even when doing this, I found a noticeable 28% increase in the volume of reinforcement I needed to meet the Krackworth requirements. And this increase was mostly fueled by the need to provide additional side face reinforcement to control cracking on the side faces of the beams. For the crown wall units, Y20 bars at 200 to Y16s at 125 in the critical restraint zone. And that's the zone where you can see the green rebars in that diagram on the right. But for these crown wall units, the effect of the crack width requirements was fairly limited. We only saw a very small increase in reinforcement volume of 5.7%. And this was because in this case, we had relatively small restrained thermal and shrinkage movements. But what are the effects of option 1 on durability? And sorry, I'm just going to grab a quick bit of water. So the graph you can see in front of you is a graph of service life for the members designed with and without the crack width requirements. And from this graph, we can see that at best, the use of option 1 results in the same service life as not using the crack width requirements. However, in the worst case, option 1 actually decreases or results in a decrease of service life. And this is because using smaller bars smaller bars are less robust and they are prone to higher corrosion rates when you pack them closer together. And this means that from a durability perspective, option 1 is really not recommended. And option 1 is also not recommended from a cost perspective, because when considering the full life cycle cost of the member, for the beams, it would be cheaper to simply not design for the crack width requirements. And for the wall units, it would be cheaper to use another option of providing durability, such as a crystalline admixture or a hydrophobic coating. And the same can also be said for environmental sustainability. The use of the first option can result in significant increases in environmental impact through the use of additional reinforcing steel, or significant amounts of additional reinforcing steel. So again, option 1 would not be recommended from a sustainability perspective. And this means that option 1 is from a durability, cost, or sustainability perspective. And overall, this suggests that reducing bar diameter and spacing to meet the crack width requirements is really not advisable. So what about option 2? If we want to use option 2, and increase the provided reinforcement area, there are 3 ways we can do so. We can either keep the same size bars, but reduce the spacing between the bars. We can increase the bar diameter, or in critical cases, we might have to reduce the bar spacing and increase the bar diameter. But reducing the bar spacing, as we've seen, is not always practical. It can lead to constructability issues. So when using option 2, we often end up increasing the bar diameter. However, the way the crack width formulas or crack width prediction formulas are formulated, increasing bar diameter increases crack width or increases the resultant crack width, and this makes it harder to meet the requirements. And this means that option 2 will often lead to large or even excessive increases in the provided reinforcement area. And this can best be seen by plotting the provided reinforcement area against bar diameter. And that's exactly what I've done for the jetty beams and the crown wall units. And we can see, particularly for the Model Code 2010, which has a very strict crack width limit of 0.2 millimeters, that using option 2 results in excessive increases of volume. For example, or reinforcement area of up to about 200%. So overall, option 2 may result in large increases in cost and environmental impact through the use of additional reinforcing steel. But when it comes to durability, option 2 shines, because by using larger bars, which are more robust and tend to have lower corrosion rates, option 2 will actually have a favorable effect on durability. And this is particularly true for the Model Code 2010, again because of the millimeter crack width requirement, but here it actually acts in our favor. So in conclusion, on option 2 would actually be recommended from a durability perspective because it can increase service life, but it would not be recommended from a cost and sustainability perspective because it can result in large increases in reinforcing steel. And overall, this suggests that increasing the provided area of reinforcement is a valid way to increase service life, but comes at a high monetary and environmental cost. So in summary, neither of the 2 options are actually particularly inspiring. At best, we can increase service life at a higher monetary and environmental cost. And I believe this is because the crack width requirements are deeply flawed. They do not prevent corrosion, and they may only slow it down. And that's in the best case where there is actually a relationship between crack width and corrosion rates. If there isn't a relationship, then all of this is pointless anyway. But the crack width requirements may slow down corrosion enough to achieve adequate service life. But is this really the best we can do? I don't think it is. Because I believe by failing to prevent corrosion initiation with the crack width requirements, we're actually surrendering a large component of the total service life without a fight. And I think a much better way of dealing with the effect of cracks would be to adopt a more relaxed crack width requirement, simply to prevent excessive cracking, and then focus more of our attention and resources on the use of measures which prevent the initiation of corrosion entirely. And these measures could be repairing cracks after construction and as part of routine maintenance with crack sealing products, or we can also use crack sealing admixtures, waterproofing admixtures, such as crystalline admixtures. And we can also use hydrophobic coatings to the same effect and to prevent moisture from being present at the cathodes and therefore prevent corrosion. My favorite of the options, we could use inert reinforcement such as basalt rebars, which doesn't have the potential to corrode in the first place, so we don't have an issue with corrosion at all. But importantly, before any of these alternative measures can be adopted, their use first needs to be comprehensively validated. And to do this, we'll need further academic research on the long-term effectiveness and durability of crack sealing products, crystalline admixtures, and hydrophobic coatings. And further research will also be needed to validate my findings, particularly on the effect of crack width and bar diameter on spacing on corrosion rates, and particularly for real marine reinforced concrete structures, because most of the current studies have just been studies conducted in labs on very small beam samples with maybe only one reinforcing bar in the sample, which is a very different situation to what we actually have in real structures with lots of reinforcement going in all directions. And I also believe we have quite an opportunity because we have a wealth of existing structures all around us, some of which were designed with the crack width requirements after the 1980s, and some of which were designed without the crack width requirements before the 1980s. And I really think there's a lot we could learn from investigating these structures. And there's some precedent for this. For example, some researchers in Norway who did an evaluation of a number of different structures, the coastal structures in Norway, actually found that there was no difference in durability or service life between structures which were designed with or without the crack width requirements. And I wonder if we couldn't find a similar thing here. But what might such an investigation look like? Well, I've actually carried out something like that investigation for a jetty in the Mons New Harbour. And from the lessons I learned from that evaluation, I've put together some steps of how we can carry out such an investigation. The first thing would be to locate a suitable structure. And it turned out the Mons jetty actually wasn't very suitable because the structure had high enough loads to be cracked in service. So when carrying out an investigation like this, the first thing we need to do is make sure that the structure we're looking at is under high enough loads to actually be cracked. If we're sure of that, then the next step is to investigate the history of the structure. And particularly important is to know when the structure was built, because from the date it was built, we'll know whether it was designed with or without the crack width requirements. Then, if possible, we want to also analyze any available design info or drawings so that we can estimate in-service crack widths. And once we know what the in-service crack widths will be, then we can evaluate the actual condition of the structure and compare that to the predicted crack widths and come to a conclusion about the effects of that crack width on corrosion. So, in conclusion on what we think, the current crack width requirements have provoked significant criticism in the literature. And in practical terms, the design of marine reinforced concrete structures to meet the requirements boils down to a choice between two options. We can either reduce the reinforcement diameter and spacing, or we can increase the provided area of reinforcement. But neither option is actually particularly attractive, although the second option may potentially produce large increases in service life. And I believe this is because the usefulness of the current crack width requirements is limited by the fact that they do not prevent corrosion. At best, they may only slow it down. And I think other methods, which prevent the initiation of corrosion will likely be more effective and more efficient than the current crack width requirements. However, more research is needed to validate these other methods, and more research is also needed to look at the effect of bar diameter and spacing on corrosion rates. And ultimately, I believe there is a great opportunity to learn more about the effectiveness of the current crack width requirements by looking at existing structures. And these are just a couple of the references. And then I can conclude on my presentation. So we'll just have a quick 5 minutes comfort break, and then we'll get started with the discussion. And thank you all for listening to that so far. I'll see you in 5 minutes. For those online, I think we're going to give it until 10 to before starting again. So it's 10 to 5. I think we'll start off again with the discussion session. So this is going to be a workshop on the crack width requirements in practice. And there are 13 talking prompts that I've included for this discussion. The first is, are there any questions on my research? And no need to try to hold back, hard questions or anything. I'm open.
There's a question from Dane.
Okay. Dan, you can go ahead.
Hi, Nicholas. How are you?
Hi, Dan. I was told to expect hard questions from you.
Yeah, thank you very much for the interesting presentation. I see your research kind of considered on increasing rebar quantities and spacing and changing diameters. But what was is there any indication of what the benefits would be in simply changing the section size, and how that compares to adding additional rebar and spacing constraints?
Very good question. I didn't actually look at that, and I think that could be possibly a more efficient way of using the requirements. And
yeah, because what I generally find is that we as engineers we immediately try and design for the ultimate limit states, and because we're so scared of this structure collapsing, so we focus immediately on the ultimate limit states. But for marine structures, I'd say 75% of the times the serviceability limit states actually govern the designs and what section sizes we put into practice. So
absolutely.
I think maybe a reversal in the way we approach the engineering to marine structures would help us sort out a lot of the issues that we face in suddenly having to make a decision between increasing rebar quantities to the point where it's impractical, and potentially introducing more issues when this thing actually goes through construction.
I agree. It's definitely a good way to look at it. And that was actually going to be one of the talking prompts later is, are there any other ways around the crack width requirements that those in the audience have used? And yeah, I think that's a very valuable point to make. So thanks, Dan. Cool. Any other questions?
Yeah, I've got a litany of questions here. You say that the model code or the FIB codes are potentially going to be replacing our current understanding, or how can I say, codified requirements to design for crack widths. But I'm quite interested in the regional implications of that, especially when we as marine engineers design to marine codes of practices. Do you think that codes like the BS 6349 and the Abu Dhabi Marine Code of Practices, for example, and PIANC will onboard these new requirements in crack widths, especially when we know that there's a very clear economical link between a crack width and the actual cost of the structure?
Yeah, I think that's a very good question, and one I'm not entirely sure I can answer. I can't be sure what's going to happen with other codes of practice, but what I do know is that in general, the FIB model code is used as a sort of baseline for most codes of practice. And it'd be very interesting to see what comes out of the FIB model code 2020. Unfortunately, I haven't been able to look at that yet. I think it is, well, the draft version is going to be published sometime this year, and I think that will be very interesting. But it's important to note is from what I've read about it so far, there will still be crack width requirements in that new model code. So I don't think we'll necessarily be getting rid of crack width requirements anytime soon. And yeah, I don't think they'll be changing fundamentally anytime soon, unless I have something to say about it.
Sure.
Nick,
Yes.
on the sustainability side, when you do the sustainability check, does it account for the increase in design service? Because you said you throw in reinforcement at it to get the design life.
Which you don't always get, depending on which option.
So you increase, which has an impact on sustainability, but you increase the design life, so you're not.
Yeah, to be honest, I didn't look at that directly. on the product stage, that's the emissions associated just with mining the material for the rebar and the concrete and manufacturing it. That will of course have an impact, but I want to point out for the life cycle costing, I did look at that impact. So the costs account for that impact, just not the environmental sustainability component.
Dane?
Yeah, Nick, you know, the common thread behind durability issues, I mean, strictly speaking, we wouldn't really care about a crack width or a serviceability limit state crack width unless there was a correlation with something that it's affecting, right? And the bad guy in the story here is the reinforcement, right?
Yeah.
I mean, so I think, and I'm quite interested to hear from the broader floor in the meeting, what is the perception of removing steel reinforcement altogether from marine structures and replacing them with basalt reinforcement, or let's say, you know, alternative means of reinforcing concrete, so that we don't have to deal with the actual bad guy in the room. We remove it from the situation altogether, and we can design structures which, for lack of a better expression, have an infinite design life, you know, reaching 200 years. So is it a function of us not understanding the implications of using alternative materials such as GFRP bars, or you know, polyethylene, polypropylene fibers to try and bridge cracks and try and close those cracks? Because I generally see that there's a big hesitation in the broader community to pivot and to use alternative materials like these.
I
So
think
I'm quite interested to hear from the rest of the guys sitting in the meeting.
very, very, very good question. I think before I open that up in the meeting, I'd just like to add from my side that here at PRDW, we have been looking at using basalt reinforcement recently, and on some of our projects we have used it, but we're also quite skeptical of it. We've only used it for dowel bars and sort of less critical members, because I think in general there is that hesitancy to use something new, particularly when you're so used to using steel. But I very much agree with you that we could actually avoid the problem completely using alternative methods. Or, yeah, we could, if possible, even use no reinforcement at all. You know, for certain structures, maybe we could do that. I definitely think that's a good way around it. But I think let me open up the floor to anyone else who has experience with using alternative methods of providing durability and strength to structures.
I think a lot of when you're looking at economics and availability, big issue.
Very true.
And then the importation of something that as well, which is obviously has a sustain, although it might be to produce it less low carbon.
But if you're having to transport halfway around the world,
the
big
carbon count,
yeah.
It's not actually. So there's a number of factors, but I think it's definitely opening up.
I agree.
It's definitely, and the availability is improving. So maybe speaking more from a South African context, but yeah, it's definitely something we can consider all the time.
Yeah, very much agree with you, and I think it's something we're going to see more and more in the future.
I think there's a lot of value in that, and I agree with you. Currently, the availability is the issue, but I think that will improve. But I think that one can also consider where you put those bars in.
Yeah.
So you can maybe keep your traditional steel, but in those most exposed areas, you put the fibre reinforced bars.
I agree.
Bars.
And finding that balance. I suppose also in codification. Other thing.
Yeah, at the moment, the options in codes of practice are quite limited for alternative methods.
So if you're having to try and comply with something and you're trying to bring a product in, but you haven't got the codification behind it, it's just
very difficult.
So then you might have to introduce R&D to back up the introduction
of course. And it'll be interesting to see what approach the new FIB model code takes on that, and hopefully it'll account for that more.
I think from my side, it's also a risk thing, right? We all try to manage our risk exposure, and we We naturally, engineers are conservative by nature, so we try to stay away from things that we do not fully understand. So I think the more acceptable the use of other inert materials become in reinforcing concrete, the better and quicker engineers will onboard the process. So obviously the material isn't available because no one's using it. But I think if the narrative behind using inert materials changes and it gets introduced at the grassroots of engineering practice and engineering how can I say, learnings, then I could see that landscape could shift very quickly. I think a big challenge also is trying to convince a client, because I mean, at the end of the day, it's client versus cost, right? So normally a client can't see further than 10 years and the initial capex investment that they put into their structures. So I think the durability question is being fought on all fronts, one from a technical perspective and one from an actual client versus cost relationship as well. So there's a lot to fight.
I agree, there's lots of angles. And also I agree with your point that we should maybe start teaching about the use of some of these alternate materials at university. And yeah.
Look, I mean, I think there are already codes of practice that are utilizing basalt rebars as part of a technical offering. The ACI has a code of practice for that. I believe the Australians have also recently introduced a code of practice for that. It's just a matter of, having that ability to apply those codes of practice properly and having the literature ready to try and convince clients that this is probably a much better solution in the long run compared to a very upfront capex cost.
I agree. Yeah, I think we need to back it up with more research, and also I think with more experience we'll effectively just get better at designing using alternate reinforcement.
There's a question from Vilja asking what is the availability natural resources of any alternative, and is there anything that could replace reinforcement in that kind of scale?
So very good question. I think I can answer from my little bit of experience with basalt rebar design, is that it is becoming more available in South Africa, and basalt rebar is actually quite an interesting material because it uses basalt rocks which are then heated up and made molten, pulled into strands, and then those strands are put together in a resin matrix, and that means that the main material is actually basalt, which is basically just a rock which is very, very abundant. So I'd argue from a sustainability perspective, that's a lot better than using. Although of course it's still a manufactured product, and in that resin there might still be sustainability issues as well. But I think there's a lot of potential there, and I think sort of commercially on the market will also become more and more available in future. So I think it's definitely something we'll see more.
Nick, another thing to consider as well is that if an alternative material is used, what is the implication on the structural safety or the ability of that structure to be ductile, right? So I think that's why there's a big hesitance in using GFRP replacements or basalt replacements, and that reinforcement becomes very brittle, and you lose your reliability in your structure, which is effectively drummed into us as engineers through the codes of practices and our teachings. So I don't think that the answer is specifically complete replacement of steel. I think there's more benefits in having a composite approach, maybe having the GFRP bars in the periphery of the member and ensuring that you achieve your ductility through providing more conventional reinforcement within the section, away from the exposure zones. that's probably a feasible solution. But I certainly don't, and I think it's probably more, how can I say, appropriate for more redundant members, like capping beams, which don't necessarily need a whole lot of ductility to perform their function. But it's when we're looking at, let's say, deck on pile structures and piers and jetties that are a clear slab and beam system, then I suppose you would be wanting that ductility from a code of practice perspective, and a safety and a ability to sleep at night.
Yeah, I agree 100%. I think it might be a bridge too far to actually use basalt or other FRP reinforcements completely as a complete replacement. But as you mentioned, definitely more redundant members and sort of in members like those crown unit side design where they're not really fulfilling any structural purpose, but we still need a certain amount of reinforcement there. There, I think we could use a lot of basalt or other FRP reinforcement.
Yeah. I see you have a talking point number 3 for the engineers. What guides your choice on bar diameter?
Yes.
To me, that would be what I've been taught. I find a lot of the times I lean back on the teachings from my mentors, and if it's not Y20s at 150, then the structure's probably wrong.
Sounds about right. That sounds like full talk.
Yeah, that's a Phil Smith teaching, right? So if it's and to be quite honest, it makes a lot of sense, because I think if you start heading into the 125s, the 100 mil spacings, your rebar becomes very congested, especially with the type of loads that we normally have on marine structures. So normally going closer than 150 mil spacings, irrespective of the bar type, you need to start looking at whether or not you have the right geometry for the section.
Very, very good points, I think. And again, to your first point, I think that's something we could maybe look at more in the future, is not just having the two options of smaller bars, closer spacing, or more reinforcements. Geometry changes might actually be the best way to deal with this problem. But thanks for it.
Yeah, and then you've got point number 4 there. Have you seen a correlation between cracking and corrosion? No, I don't think I've been alive long enough to see my structures corrode. So I don't know if that's a blessing or a blessing in disguise, but I don't necessarily think so. If you look at how the BS6349 has developed, and the BS8110 and the Euro codes, and especially the BS8007 for water retaining structures, there's a very inconsistent recommendation on what is deemed to be a compliant crack width, right? And we go from 0.1 mils, 0.15 mils. All of a sudden, the Eurocode tells us no, 0.3 mils. So there's big inconsistency, and I think that inconsistency isn't bad information to use, right? It just shows you that if you are sitting at a 0.4 or 0.4 crack width, you're probably not going to see significant structural deterioration, given the inconsistencies in the recommendations from previous codes.
I agree.
So I think the most important thing, especially for a marine environment, is to get your concrete specification correct. Instead of worrying really about the nth detail on the crack width that's coming out, because these are theoretical calculations, and that 0.3 only represents the average crack width. So you could have crack widths that are actually larger than 0.3, right? So I think the crack width needs to be seen as a checkbox exercise, but you should be focusing on things like concrete cover, making sure that your cover concrete is dense, making sure that you have the right mix parameters, and especially above all else, having the right performance on that concrete mix. Doing your chloride test and doing your penetration tests and all of that, and making sure that the clients understand what the benefits are in terms of introducing some performance testing or performance specifications to their concrete mixes.
Again, I agree with you, some very good points, and I think it should be just a box ticking exercise, but I think the reality we're seeing is that it often isn't. It ends up governing the design, and it ends up using a lot more reinforcement, which I think is counter to the point. And sort of what you were alluding to, we are going to get cracks bigger than 0.3 millimeters anyway. And, you know, going back to when I was actually doing my research, looking at the predicted corrosion rates between a 0.3 and a 0.5 millimeter crack, there really isn't actually that much of a difference. And also, I think an interesting point you raised with the variability in crack width limits, I think that's a reflection of what I mentioned about there being no clear relationship between crack width and corrosion rate, because each of those codes has used different research to get that limiting crack width value, and so they each have a different result. And that's because I don't think there is any clear relationship. If there was, there would be just one value clearly that everyone's agreeing on.
I think if you had to dig into it, I think a lot of the issues, if you look at the structures that have big issues, it's going to come down to you have the best specs, the best designs, but it's going to come down to the contractor.
Absolutely. I think that's a lot more important.
Yeah, and high quality mix, but not compacted properly. Not the right cable blocks. That's, I think if you had to research the structures, potentially you would find that the end product is an issue.
Absolutely.
A big driver of the corrosion.
Yeah, and I think it'd be very interesting to actually a lot of different structures and durability problems and look what was the cause of that problem, and then kind of compile that. And I think you'd find cracking probably wouldn't feature.
Yeah, I think I can add to that as well. I absolutely agree with Dane and what Sean was saying. I've seen a lot of corroded reinforcing in the fishing harbours, and I think the bulk of those issues are not so much cracking issues, but the cover and the concrete quality.
Absolutely.
Issues. And therefore the steel corrodes and therefore it cracks.
Yeah.
It's not the cracking.
It's not flexural or shrinkage cracking.
Just one thing on the crack culture, it's also making sure you use the right load for the crack width culture.
Yeah, it's very sensitive to that.
Yeah.
I agree.
Quasi
Yeah.
what is often.
Yeah.
Even that, Sean, you make a very good point. I mean, a lot of the times we just set everything to one, and we make we don't necessarily realize that our serviceability load for cracking is actually a lot less, right? So we tend to try and be as conservative as possible, but the fact that we aren't making how can I say, making use of things like quasi-permanent situations is a big drawback, and it will then obviously lead to being more conservative in the steel that gets put into the structure. But I think the flaw there is that it's very difficult to quantify or to rationalize what a quasi-permanent load combination is, because all we're effectively doing is we're taking what was once 100% of the load, now all of a sudden becomes 30-50% of the load. So I think again it's our ability to convince ourselves that we need to remain conservative in all things design because of the liability issues associated with it. So
yeah, and if you are bound to do the check, do your ULS checks. Do your SLS checks, size your member, get your pass spacing right, and then don't go through all the ULS calcs and then get to the end and do your SLS and realize you're going to rejig your whole structure because you're not SLS check.
I think very good point. I think that we should look at SLS more than size of the members, because usually, from my understanding, the members are sized based on
particularly because they're so conservative.
Yeah,
I think. Yeah.
And you've spent all your budget by the time you've gotten to the SLS checks. so then you're forced to be conservative. Yeah.
Okay, so I think that's been a very interesting discussion so far. I'd also like to hear more from those online. And please don't be shy if you have any questions or comments. This is only the first 5 of the talking prompts. We will move through to the rest later. What I'll maybe ask is, does anyone in the audience have any horror stories of, noticing severe corrosion as a result of cracking?
It's quite interesting. I showed you those photographs of that Key and Pepper Bay where those planks, big planks, were clearly not designed adequately. So there was a lot of cracking, but actually not a lot of corrosion.
Very good point. Yeah, and I mean, that isn't necessarily proof of anything, I think, because there could be corrosion that you can't see. But the fact that there is no visible corrosion, I think, even those cracks were like 1 or 2 mils wide, they were massive. I remember those photos. I think that's an interesting find. Interesting point to make.
Yeah, Nick, in terms of number 5, if you go look at sites and you're inspecting a deteriorated structure, when you get there, you don't necessarily see cracks. What you see is spalled cover concrete and rebars that are effectively already well corroded. So I think it's very difficult from a practical perspective, especially from an visual inspection perspective, to really nail down if it's the crack width that's 0.3 that you can barely see with your naked eye that's causing the crack. And to me it kind of suggests that, again, cracking isn't necessarily the mechanism that's driving corrosion or durability issues. It's because you're seeing widespread spalling and widespread corrosion on your structure, it's most likely the concrete cover and the quality of the concrete mix for its given exposure criteria. So in my 13, 14 years of being a marine engineer, I've never seen a direct correlation between crack width and corrosion. When we get to site and we see these structures, there's, it's so badly deteriorated that it's very difficult to really ascertain if it's a crack width. And more likely than none, you'll see that there's cover that's like 40 mils, 30 mils. Which just isn't going to cut it.
Yeah, I think, I've asked that question, but I don't think that there will actually be many such horror stories. And as you said, it is very hard to pin down the cause of that poor durability, but that's also where I think we could really learn quite a bit if we have structures that we have design info or as-built drawings for. Then, as I mentioned, we can actually predict a crack width for those structures and then compare that to the. And we can also look, for example, for jetties, we'd expect to see corrosion due to flexural cracking at the soffits of the beams and the slabs.
Yes.
And, if we see a clear correlation between corrosion and the areas where the reinforcement is most highly stressed and where the moments are greatest, where the cracks will be greatest, then I think we could learn something from that. We might be able to see a correlation. But yeah, I think from inspection, it's very limited what you can actually ascertain.
There's a hand from Scott.
Scott, go ahead.
Good day, gents.
I
agree 100% with Dane. I specialize in the rehabilitation of concrete and marine structures. There are very few marine structures that are suffering with corrosion and spalling due to crack widths. Remember, as engineers, you work according to an exact science as far as your designs go, your concrete mix design, and the theoretical design of your structure. There's one person you are leaving out of this equation. That is the guy that places your concrete. That is by no means an exact science. They deal with programs that they got to rush. They deal with adverse weather conditions, and I can almost say 90% of the cases, your concrete that is well designed, your structure that is well designed is not placed according to your design. And that is where the problem creeps in. You've got reduced cover in areas. In fact, I've seen structures where there is almost zero cover. And we need to take that into consideration as well, by getting that limited cover as dense as possible.
Yeah, I couldn't agree more, and thanks for that input, Stork. I think we spend so much time designing the structures to be perfect and making sure our crack width is perfect. And then, as you mentioned, when it actually gets built on site, it's not built properly. And then all that extra steel we put in there to limit crack widths is like just more fuel in the fire that's going to corrode anyway if it has poor cover. So thanks for that input. I think very good point.
There's another hand from M. Rebel.
Sure, go ahead.
Yeah, Nick, thanks for the talks. Definitely very interesting information. But yeah, I don't want to be a broken record, but I think I agree with Gus and Dan and all the others who are saying, like, I think a lot more can be gained in terms of corrosion prevention from like just good control in terms of concrete cover and also the mixed design itself. But obviously then same along with that is also supervision on site, because you know, a lot of the times the guys, like maybe the foremen or construction managers, they're well aware of all the requirements in terms of cover and that sort of thing, but the guys actually doing it, they maybe don't really understand what the implications are. But having eyes on the ground there and actually checking the things is almost just as important as well. But yeah, and I think that sort of composite sort of design where you have alternative reinforcing combined with steel to making sure that the structures are ductile is probably, I think, the way that it's going to be going forward. Well, in my perspective, yeah. And also, yeah, I think the crack width or the horror stories mostly is, I think, also due to like, yeah, mainly I think low concrete cover in general, with the cracks probably just fueling the fire. Because I think I'm probably from the school of thought that thinks that there probably is some form of relationship between crack width and the corrosion in the long run. Maybe in the short run, maybe not so much, but I think it's probably affected as well. But yeah, I think the concrete mix design and like new technologies that's around in terms of making the concrete more dense and that sort of thing, and or self-healing, that sort of stuff, I think more, yeah, like from taking that into consideration in durability designs and that sort of things is, I think there's big advantage in that. But yeah, thanks. Very good work.
No worries, and thanks for the inputs. I agree with all of that, and I think definitely better construction supervision, more focus on other areas of durability design and use of new technologies. I think that's the way to go, rather than focusing on crack width. And yeah, I think that's in many ways what I was trying to say. So yeah, thanks.
Yeah.
Thanks for the input.
There's a hand from Dan.
More hands? Dan, go ahead.
I think we've failed to touch on what I think is a golden egg when it comes to you know, reinforced concrete design in the marine environment, and that's galvanized rebar. I think galvanized rebar is completely overlooked in our industry, and it's perceived that it's an expensive thing to do. But what it really is it's a happy medium between using conventionally reinforced structures and providing those structures with an extra overprotection that is really good. So I mean, if you really think of it, all the technical knowledge is there to utilize galvanized rebar. It's conventional rebar, just with you know, it being galvanized, so we don't have to learn anything new. And it really provides a good protection to the rebar. I mean, if you look at the V&A swing bridge, that whole foundation system is a galvanized reinforced cage, which I think is an awesome initiative. What additionally what it also allows us to do is actually find, you know, correlations to reduce cover concrete, you know, because you are providing the galvanization, and in turn that reduces your crack width, right? So when you're trying to satisfy crack widths, smaller cover is obviously a game changer because of the way that the theories are formulated. So if the use of galvanized rebar allows us to reduce cover and improve, the durability of the entire system, then I don't see. It really baffles me why it hasn't been onboarded more. I mean, the only real drawback I can think about is an extra step in the procurement process, maybe a little bit more upfront capex, but that is offset by your maintenance procedures that you need to put in place when your rebar starts corroding, and probably some concerns about bimetallic corrosion. But I mean, even if we use galvanized rebar in the outer layers of the reinforced concrete members and use conventional rebar somewhere else in the member, I mean, I think there's a lot of benefits to galvanized rebar.
Very, very interesting points, and yeah, I do wonder why it's not used more. My perception of galvanized rebar is also that it's very expensive, and I think, I'm sure maybe someone in the literature has done this, but it would be very interesting to see a life cycle cost comparison of using galvanized rebar versus using just regular rebar. And also, I think a very good, if we could reduce our cover depth, then yeah, that's going to have a major impact on crack width. And it would be interesting to see a life cycle cost comparison of that.
There's a question from Patrick. Are all these rebar materials alternative as ductile as conventional steel rebar?
I would think that galvanized rebar would be, but the issue with some of those fiber reinforced polymer alternatives like glass fiber or basalt is that they're not really ductile at all. Their failure is very brittle. And that's what Dan was alluding to earlier when talking about how we have very brittle failure in those kinds of, or structures reinforced with those kinds of reinforcements. And that's, something that I think a lot of engineers shy away from using that kind of reinforcement because of that issue. I think we move on to the next series of talking prompts.
Oh, there are more.
There we go. There's plenty more. I was worried you wouldn't have enough to talk about. But no worries if we don't get through all of these. First question. Have any of you noticed any correlation between bar size and corrosion rate or corrosion damage in real structures? Because I think it's quite intuitive that smaller bars will sort of wither away faster, but I'm wondering if anyone has any experience to back that up with.
No, I think that it's really the same as number 4.
Yeah.
On the previous slide. It's very difficult to ascertain that once the structure has started popping and everything's going haywire.
Yeah. Question I might ask of Phil, who I think is online, is that Phil's known here at PRDW for saying nothing less than Y16s, and usually if your design tells you use Y16, he says no, use Y20. We just asked Phil, what is that based on? And Phil, is that based on any correlation you've noticed, or is it generally just being conservative and being on the safe side?
Yeah, probably just being conservative. I mean, it probably boils down to a sensible bar size and a sensible spacing, really.
Okay.
Yeah.
So there's no direct consideration of durability?
No, I wouldn't say so. I mean, when we're thinking about constructability and what just feels sensible when you ending up with a cage.
Okay, I think that's actually a good way to look at it. Hearing all these points about constructability and that having a much bigger impact on long-term durability or just durability in general because of poor cover depth and things like that.
Yeah, I tend to agree with Phil. I mean, I think we know that our structures are prone to deterioration, right? So what would you do as a conservative design engineer? You'd you'd almost allow for some sacrificial steel on your rebar.
Yeah.
So I mean, if you look at the Australian Code of Practice, I think 4997, AS 4997, the Australians actually stipulate a minimum bar diameter for different components of a marine structure. So they actually say if you have a soffit that's exposed, you can't go lower than H20s or H16s. And I would assume that is to do with some type of reliability to ensure some type of reliability if something does go wrong with the concrete durability. I don't see any other correlation,
Yeah.
Okay.
I mean, if you
Yeah,
have
good point.
if you have a 12 mil bar and you lose 1 mil in corrosion, it's very different if you've got a 20 mil bar and you lose 1 mil of corrosion.
Exactly.
Yeah.
Absolutely. And that's what I was accounting for in my service life model. And so I think the two are linked because the bigger ball will take longer to lose 15% of its cross section and effectively will be more durable, more robust. Yeah, so I think definitely that's something at least I think everyone is doing a good job of.
Sure.
Cool.
I think, sorry, to just add an example of that is in Strand, where they use Y12s as connecting bars between the coat and the wall.
Yeah, they
It took 5 years before they, look, that was obviously a construction thing rather than a design issue, but it took 5 years and they failed. Whereas if you had 20 in, I promise you it'd still be there now.
Yeah, very good.
Maybe not much longer.
But I think that proves the point that bigger bars simply are more durable.
And Gus, those bars were galvanized.
Yes.
So I think because of the bad construction, they were exposed, and so they were probably acting as anodes as well.
Yeah.
Yeah, probably got a joint that was permanently wet and had a nice little anode there. It corroded preferentially and disappeared.
Yeah. No, it was certainly accelerated. There's no question.
I think that, Phil, that's also it's a good point. I mean, I think galvanized, but you got to be careful about that bimetallic corrosion, aspect of using dissimilar metals because it can really accelerate things. And we see it in the UAE a lot where there's painted base plates, especially on the street columns and things like that, and they go use mild steel bolts, and then it's just haywire.
Yeah.
But also, I mean, if we look at the construction of the Ben Schoeman dock, the decompile structure that's over there at the moment, the joint between the existing and the old structure is actually an FRP bar. And the designers at the time actually realized that if they do put a conventional bar there, that joint rotates and it opens and closes and opens and closes, it's actually going to form a corrosion hotspot, and that's why they prefer to use I think it was a 32 diameter GFRP bar, and they did some research and R&D, internal research and R&D, and they've satisfied themselves internally that this bar would perform well, and they actually put it in place, and I believe it's working quite well. So I mean, I think there's on two extremes here, right? We've got a connection, like Gus says, a connection for a capping block that's corroded in 5 years, and this actual, very well engineered joint that's performing well. Different materials, different applications.
Yeah.
I think it's important to understand how to apply it, when to apply it, and what the implications are where you are applying different materials.
Very interesting to hear. It's quite a success story, I think, and something we can maybe use to motivate the further use of FRP bars.
Yeah.
I think I'm going to skip a couple of questions here. Something I'm quite interested with, does anyone have any experience with crystalline admixtures and with crystalline admixtures being very effective? Because from my understanding, there's a perception that crystalline admixtures aren't always fully effective or aren't something that we can rely on entirely. Like they're more something that's nice to have if we have money for it, but they're not something we can base our design on. So I was just wondering if anyone has any good or bad experience with crystalline admixtures.
Yeah, Nick, from my perspective, It's normally not specified in marine projects because of the extra cost, and trying to convince your client that the extra cost is justified. Because normally they would ask for life cycle analysis and to see what the cost benefit is of introducing a new material into the offering, whereby, you know, experience dictates that you could achieve a durable structure by just providing concrete cover and proper concrete. So generally speaking, clients aren't too keen to add that to the bill. On the other hand, I'm quite a fan. I think there's some good products out there on the market which have good technical backing, good research, good testing records in the labs. It's just that it's very difficult from an economical perspective to get a client to buy into that. I'm pretty sure the academics in the call at the moment have their own opinions on this as well, which I'd be quite interested to hear from the researchers in the crowd. But I think there's definitely a benefit to applying these things to the structure, especially things that permeate into the cover concrete, not necessarily a barrier coat, but materials that go into the capillary structures of the concrete and actually densify the concrete from the inside out. I think those type of materials are beneficial. I don't think they change the crack width, the influence of the crack width, unless there's some type of healing mechanism to the impregnation. But because that crack widths are flexure, they're stress driven, so it's going to crack whether you have that material on or not. So, but I think from a general durability perspective and general penetration and trying to stop those chlorides from getting to the steel, they have a massive impact.
Very interesting to hear. I would also be interested to hear maybe some of the academics in the audience if they have any opinion. And yeah, maybe also if anyone knows of any life cycle assessments which show that the use of crystalline admixtures is beneficial, it would also be interesting to hear.
Yeah, Nick, I think from the life cycle costs perspective, I think the life cycle costs that we generally see aren't really into enough detail to really show the benefit of these sort of things, of like small things like adding crystalline admixtures, where I think they do add a lot more than what's typically attributed to them, like in these life cycle cost estimates. So I think it's maybe that part of the process must be improved a bit more to actually show that, because I'm sure it would be quite clear that it does like significantly add as well. So I think just the kind of detail of those studies, they're normally done maybe too late or a little bit too late in a project, at which point like budgets are get fixed at some point in time, and it's difficult to get more money. And it's not a case of that you don't want to, like the process has progressed to a point where it really gets difficult. So maybe, yeah, I think maybe something to consider.
Okay, so maybe something to bring into the project earlier on.
Yeah.
Yeah.
Phil, we had discussions with the waterfront about when we were talking about those concrete pontoons, etc., about applying some admixtures to the concrete. I think that discussion was also met with a bit of hesitance because of the extra cost. But again, it's also a matter of who takes liability for these things, right? So if you go to a supplier and ask them, okay, I am going to convince my client that we need to apply this product, but I need you to tell me how much I can reduce my cover by to compensate for the cost. Unfortunately, no one will. No suppliers that I am aware of will put their liability on the line like that to say, okay, you can take 10% off your cover, but it will help. So that's a very hard selling point to a client.
Yeah, and I suppose that's an unfortunate reality that no producer of a crystalline admixture is ever going to be able to say with 100% confidence that their products will prevent corrosion to the extent that you can reduce your cover depth.
Just Nick, another point to consider is also if it's a flexural crack which opens and closes.
Yeah,
Remember we had, he mentioned it today in the presentation. It's
going to open again,
it'll open.
of course.
So
Yeah.
it might be good for cracks which are, I don't know, shrinkage cracks. Or
Yeah, I think that's where there'd be a
more
better
permanent, yeah.
better application.
But not for cracks that are sort of flexural cracks.
Yeah, I think so, and that is, I suppose, one of the main areas where the crack width requirements would be beneficial, because I think there's a very limited amount that you can do to repair or seal cracks or flexural cracks. But there, I think the use of alternative reinforcement would really shine.
Look, prevention's always better than cure, right? So,
Absolutely.
and by the time you need a cure, your structure's falling into the water.
Fair enough.
I don't envy Skalk's line of speciality. Let's put it that way. I think a lot of the times when engineers get called into the fray, it's already too late. And the sad reality is that the structure needs to be rebuilt.
Yeah, I think very good points. I think it's all like very good and well saying that, okay, it would be very beneficial if maybe we use the 0.5 millimeter crack and then just seal the cracks afterwards. But is the client actually going to do that, or is the maintenance actually going to be in place to do that? Probably not, and I suppose then you're going to have an issue anyway.
But again, then it's going to come down to quality of that work, quality of that sealing. It's down to a contractor, which is outside of control.
Yeah, and I suppose it's something you can't rely on from a design perspective. That's a very good point.
Otherwise, we mobilize the tug and we do load tests.
I think though we're almost out of time here, and the other questions I have here I think aren't as critical. I think it's already been a very valuable and interesting discussion. So sort of last chance if anyone else has any other comments, questions or suggestions.
Yeah, sorry Nick, just a closing thought. I dropped a link of the resilience campaign in the chat to tie into what Skalk said earlier. Obviously there's a lot of this research is built around precast elements, where using crystalline you can reduce the cover quite a bit, and obviously because you have control of the concrete that goes onto site or is physically placed in, they're able to cut off quite a bit of the covercrete there. But I suppose the challenge will always remain with in situ concrete, where you don't really have control and you've got this influx of various bolts. But some really interesting work they're doing, especially with like slender members, so low cover, slender, high density members.
That sounds very interesting. Thanks for bringing that up. I'll definitely have a look at that link. And also a good point, I think in situ, particularly in the marine environment, is always going to be an issue because it's sort of perfect storm of all these different variables and lots of things going on which make it hard to produce something high quality in situ. I think if there are no other points or no other questions, I think we can end the seminar there. So firstly, I'd like to thank everyone for your attendance. I think attendance has really been amazing. I see we have more than 50 people online. That's so much more than I actually thought we would have and could have hoped for. So thank you everyone so much for attending. And I'd also like to give specific thanks to Professor Hans Boyshausen for his invaluable supervision of my research, to Marco Tolotti for the initial inspiration for this research and for his subsequent help with the member designs. I'd also like to thank Phil Smith for sharing his knowledge and for helping me with the member designs, and Gus Hoyen for his site inspection knowledge and photos, which were very valuable. Then also I'd like to thank Concrete Units for the help with costing the designs in my master's research. And I'd like to thank specifically Cement and Concrete South Africa and SAIS Marine for their help with invitations for the seminar. I really appreciate it. And last but not least, I'd like to thank the Harry Crosby Foundation, both for the funding of my master's research and also for what's really been an incredible opportunity to host this seminar. So with that, I say thank you. again for your attendance, everyone, and I hope everyone's learned something. I hope this has been valuable.
Thank you.
Great.
Well done.
Well done.
Good work.
It's all about the cracks. That was quite a